Okay, so we're going to talk about surface currents from here on out. And the definition of a surface current, besides the other things about being a mass of water that's moving in a particular direction, surface currents have to occur above the picnic line, or sort of at the picnic line. And their maximum depth is typically 1 kilometer, or frequently way more shallow than that. 1 kilometer is 1,000 meters. That's going to be important when we talk about Ekman spiral. In terms of volume of water that they affect, they only affect 10% of the ocean's water in terms of moving it. But when we talk about the fact that the oxygen that gets mixed in at the surface ends up eventually at the bottom of the water, it has a larger effect. So what is the energy source for surface currents? It's the wind. Wind is the primary source of all surface currents. And we talked about energy being transferred in waves before. Only about 2% of wind energy is transferred via friction into a current. So the example in the book is if you have a 50-knot wind blowing, you will end up with a 1-knot current. Unlike when we looked at waves, we don't need to worry about wind duration and so on. We're just going to use this rough rule of thumb because it's actually way more complicated than that, and you'd have to use a little calculus. There's a wind stress formula for that. Surface currents can be influenced by a variety of factors, which we will go into greater detail. Gravity, friction, the shape of the continents, land masses, even the ocean bottom in shallow areas can affect surface currents. But the two main causes of surface current, I put causes in quotes, are wind, the directions of the main wind belts, and Coriolis effect. And Coriolis effect, as you remember from physics, bends everything. So this is why surface currents begin to rotate. Like you can see in the image in the background, it begins to make sort of circular loops. So before I go into this, I guess we need to do a quick note or reminder. I'm assuming you learned this in naval science. I'm assuming you did. The naming of winds. Winds are primarily named for the direction that they blow from. And that's not true of currents. Sorry. Winds, so for example, the westerlies, which are basically between 30 and 60 degrees north and south, they blow from the west to the east. Polar easterlies blow from the east towards the west. The trade winds also blow from the east towards the west. So there's these three major wind belts. And on this diagram 7-3, you can see the two major ones. The ones that are closer to the equator are the trade winds. And it doesn't matter, north or above or below the equator, the trade winds blow towards the west. Yeah. And then the westerlies blow towards the east, and if there were polar easterlies, they blow the other way. So the surface currents in general follow those wind belts. The surface currents are given in this diagram in purple underneath the green arrows. Now, they're not the only thing that's going on, because Coriolis effect actually happens. So Coriolis effect takes the currents that are already there. I'm going to do this in green. I'll do it in dark green. And so the current, let's look at, say, the top of the gyre. The wind is blowing this way, and the current then begins to move this way. Coriolis effect makes everything bend to the right, so after time the current begins to blow this way. Now this current is going to get hit by this wind and start pushing it more that way. Coriolis effect begins to take over, and it also hits the Caribbean and begins to rotate. So we have the winds that are sort of blowing, as well as the currents beginning to move. And we end up with what we call gyres. And this map you're going to get very familiar with, because you're going to need to know almost every current on here. I'm not really a fan of rote memorization, except when it comes to this chapter. And what happens is, and you can see this kind of nicely here in the Atlantic, you end up with this current, and the Gulf Stream, and this one, beginning to make giant loops. You can see it nicely here too. One this way, down this way, and back. And these wind-driven surface currents begin to make big loops. We have one here, and crappier ones over in the Pacific. And we get what we call gyres. So when we're talking about surface circulation, we have to talk about gyres. We're going to talk about them a lot. There are two types, subtropical and subpolar. The gyres themselves affect surface currents, begin to pull things along. We're going to talk about the equatorial countercurrent, Ekman spiral, which I think you learned last year as well. as well as geostrophic currents. Geostrophic currents is probably the hardest part of this chapter. So let's talk about the gyres. The gyres are going to be the last part of this particular video we're going to talk about. These are large circular loops of water, and there are 5 main subtropical gyres, though there are more if we can include the subpolar. Subtropical gyres are basically in the center of the oceans, about 30 degrees north and south latitude. There's one in each ocean. So there's 2 in the Pacific and 2 in the Atlantic. Indian Ocean doesn't really occur in the northern hemisphere, so it only has 1 gyre. You're going to need to know all the currents of this. And there are 4 currents in each gyre. So let's talk about the 4 types of currents, and then you'll learn the specific names later. First, you have the equatorial current. And the equatorial current begins because of the trade winds. So it tends to move towards the west, and that can be north or south of the equator. And they're the bottom of the gyre in the northern hemisphere and the top of it in the southern hemisphere. Then you have western boundary currents. They travel along the western boundary of the ocean basin or along the east side of the continent. Let me say that again. Western boundary currents are called western boundary currents because they're on the west part of the ocean basin, which means, if you're looking at a map, that they're along the eastern coast of a continent. Let's classify them. You're going to need to know western boundary currents and eastern boundary currents and how they vary. Western boundary currents are very fast, they're very narrow, and they're very deep, and they are generally warm. They take the warm water from the equatorial current that has absorbed all the heat from the sun and bring it closer to temperate regions and up towards the poles. And the classic example of the western boundary current is ours. It's the Gulf Stream. In the southern Atlantic Ocean, it would be the Brazil current. Both of these are warm, very fast, very narrow, and very deep. And they're sort of important currents. Then you have the northern or southern boundary current. It's called the northern boundary current in the northern hemisphere and the southern boundary current in the southern hemisphere. They're the top of the gyre, and their surface waters move easterly. There's an arrow for this. If you get down into the southern ocean, other things begin to go on because we have the subpolar gyres having an effect too. There's a typo here. This should say eastern boundary current. Big typo. Let's fix it right now. Draw a line. This should say eastern boundary current. Let's fix this. They are also slow. Let's add all of this. They are in the east boundary of the ocean. They are slow. They are shallow. And they are wide. And they don't carry warm water, they carry cold water. So they're basically the complete and utter opposite of the western boundary currents. Eastern boundary currents in the North Atlantic would occur sort of basically from England down to Spain. They are slow, cold, shallow, wide, the complete opposite of something, say, like the Gulf Stream. In this picture, you can actually see the subtropical gyre for the Pacific. And you have your equatorial current, which, as we said, moves towards the west, would be warm. Then you have your western boundary current, the Kuroshio. If I asked you to classify the Kuroshio, you would tell me it is warm, fast, narrow, and deep. Then we have our northern boundary current. And that leads us to our eastern boundary current. Our eastern boundary current is slow, wide, cold, and shallow. So make sure you can compare and contrast the western and eastern boundary currents, even despite my typos. But if you notice also on this diagram, right in here, let's make this, okay, we have another type of gyre. We have the subpolar gyre. The subpolar gyre is really just 2 currents, and part of them is also part of the subtropical gyre. They're smaller. They're really only of main importance in the northern hemisphere. They have a smaller effect in the southern hemisphere. And they kind of flow in the opposite direction. So remember, our northern boundary current here was the North Pacific current. and it's part of this gyre. Why do we care about the subpolar gyres? The subpolar gyres give rise to unique climactic effects, like the Bering Sea has very rich fishing and unique characteristics compared to the rest of the ocean. Places where there are subpolar gyres frequently have very good fishing. They have the cold, nutrient-dense water, and they also have a lot of oxygen and things like that. So the subpolar gyres are tend to be of importance when it comes to fishing. One thing to notice, remember this, the subtropical rotated clockwise. The subpolar rotates counterclockwise. We're actually going to stop there for currents. For surface currents, we'll talk about factors that affect them in the next video.